our calendar. I just put a link under today's your meeting chat box there. The link for today's for our units. So if you click on that link, it'll take you to the chapter 5, 6 integrals page. Make sure that you're clicking on the integrals chapter 5 and not the derivative chapter 5. So have it in chronological order. So chapter 5 from first semester. We're still looking at chapter 5, but we're just focusing on the antiderivative sections. So I also have on that page this calendar that you can see the homework assignments as well as the upcoming day's schedule. We're going to spend today, tomorrow, and Friday going over new material for integrals. Now, we've seen these derivative rules. We've seen derivative rules for natural log. We've seen the rule for e to the u. We've seen derivative rules for a to the u and log base a. But now we're just working backwards. We're working backwards from those derivative rules using antiderivative. And we're also going to be building on top of U substitution that we did with our first section, with the last test. So it's going to feel a little more challenging with U substitution because we're going to be adding more methods, more locations where we can look for the U value. The U value sometimes is not as easy to spot as the earlier types of problems. So, and sometimes it does require a little bit of kind of guess and check to get to where we need to be. I think we should be able to get done with our new material by Friday. Tomorrow, this topic is not very long, so we can maybe get some head start into 5.5. But we'll have a review day on Friday, second half of Friday, and we'll also have a full review day on Monday. And on Tuesday, we're just going to have a quiz just over finding antiderivatives using these rules and just making sure that we can have that foundation before we move to the rest of the unit. After that, we're going to have a good 2 weeks to work these differential equations. It's a lot more involved. We're going to have to work on both sides of our equation, and that's just going to extend the problem. It's going to make the problem look more complex, so we need some time to do that. Slow fields, inverse trig, so there's still quite a bit from chapter 5 and 6. We're kind of merging the topics that we need to see from both our those units, and that will be, we're going to have a test over those select sections from chapter 5 and 6 at the end of this month. Now, believe it or not, that's going to bring us to our final unit, chapter 7. Chapter 7, just giving you a preview for the rest of the semester here, is going to be going over area volume. We're just doing a couple of sections from chapter 7, but enough where we're going to need some time to process that, and we'll have 2 weeks to work on that. We'll have a test, and that will end our final new material test. And we're going to start our AP review before spring break, okay, at the middle to the end of March. You may be thinking to yourself that this is kind of early to start AP review, but I think well, every year I try to start AP review before spring break, but I think it's also good, especially this year, that we're starting before spring break because of the way this year is set up, I kind of had to pick and choose the most important topics that I wanted to do first semester. So as we go back and review, we're going to kind of pick up some new things that I didn't get a chance to get through or to get to the first time around. So we're going to review, but we're going to pick up some new things along the way. And those are going to be important topics that we need to have for our AP exam knowledge. I'll have a couple of, we're going to have a couple of quizzes just to kind of get some of that FRQ topics and knowledge, just get our feet wet with FRQ problems. And that will lead us into spring break. And after spring break, we have that second part of April, and we're going to start preparing to take our mock AP exam. The mock AP exam, I'm going to count as 2 test grades. Right now, I still don't know the full format of the AP exam, but all I know right now, it's probably going to be closer to the standard AP exam with free response and multiple choice, rather than last year's, which was just kind of a condensed version of the AP exam with just 2 free response questions in only 40 minutes. So I'm going to prepare for the longer exam, and then hopefully by the end of this month, we can gain more clarity as to what our exam is going to be like. But I'll count this as 2 test grades. At least that's what I'm thinking now. But these 2 test grades will be graded like the AP exam, so it'll be a heavy curve on the AP exam. On this pre-AP test, just like your AP exam. So what I mean by heavy curve is it's like 25 or 30 points, 25, 30-point curve. Pretty significant, but also a good representation of what your AP exam will be like. So just to kind of give you an idea, to earn a 5 on the AP exam, on the calculus AP exam, it may be different. And also it's slightly different from year to year, but this is the pattern. If you can get around a 63 to 65%, that's a 5 on the AP exam. If you can get 50% of the problems right, that's a 4 on the AP exam. And if you get like 38% of the problems right, that's a passing grade. That's still a 3 on the AP exam. And that just goes to show you, though, that these problems on the AP exam pretty significant. You're not going to have any easy problems like find the derivative of 6x squared. Okay, it's more significant than that. So just to get one problem right requires pretty good knowledge of multiple steps required. So that's why I think it's good to have a month and a half to kind of get used to what AP problems could look like, so that when you see it, you can move through it and you're not looking at it for the first time. So after that, we're going to, after we take our pre-AP test, hoping that I can use this week to kind of go over those problems so we can kind of get this understanding the problems that we missed and trying to get some final review. And then that's going to lead us to that first Tuesday of May, which is our AP Calculus exam. We don't know whether it's going to be in person or online or a combination of both, and students get to choose. We're still waiting on College Board to give us that. But I'm thinking that if the administration is okay with just us ending with this and not having to do anything after, then that's maybe what we'll do. But we'll figure out if there's anything else we need to do to fill in the rest of the time after the AP exam. But that's as far as I know. And then you guys don't have to take the final exam as long as you've taken all the assessments leading up to this point. So you should all be able to exempt out of the final exam. Okay, any questions? All right, so today we go over natural log integrals. I want to connect this with something that we already know how to do. So I want to ask you, what if we attempted to apply power rule for this particular problem? Integral of 1 over x dx. How would you set it up to get it ready for power rule?
X is the -1.
X is -1. Okay, so let's explore what happens when we try to do power rule for this problem. Okay, what's going to happen to my exponent?
Subtract 1.
Add 1. So x to the over 0. All right, what's the issue here? Undefined. Good. So we see with our own eyes that there's an issue. There's an issue with this particular setup if we want to do power rule. Undefined. So what I want to demonstrate to you is that if you have a rational expression, any power is good with power rule, right? We're not going to get the 0 to show up in any other case except when there's an x to the first power in the denominator. So we have a special case to handle this one instance that power rule is not able to handle. And that is with this natural log integral rule. If I have 1 over x or 1 over u, just think that, all right, you can always go through power rule first and realize that you're gonna run into an issue, and then you can know that this is the one case that can handle our power rule exception. But that also means that we can't do natural log rule unless it's u to the first power. If it's raised to any other power, if it's u to the 1/2 or u to the 1/3 or u squared, we got to bring it up and go through power rule. Right. Now, first semester, we learned that the derivative of natural log is u prime over u. So first semester, we learned, here's a simple example. If f of x equals natural log of x, the derivative of natural log of x is u prime over u, which is 1 over x. And then it stands to reason, then, if my derivative of natural log of x is 1 over x, then the antiderivative should bring me back to natural log of x. So this form matches exactly with the form that is causing us an issue with power rule. So this is the new rule that we're going to be practicing today. The one case that power rule is not able to handle. Okay, so let's look at example 1. And we're going to build on our integral checklist from chapter 4. I'm going to put on a separate sheet here just to give more room and easier for you to see. All right, first things first. Whenever we see an antiderivative problem, we always want to ask ourselves, can I just move things around and rely on power rule conditions to get me to where I want to be able to find the antiderivative? Are we going to be able to resolve all these issues just by moving things around with this problem? What do you guys think?
Can we just move the bottom terms up?
So here's the issue. If I move the bottom to the top, it's going to be something like this. It's going to be like 2x x squared plus 1 to the negative 1. And we're going to be stuck not being able to expand because this negative 1 is unresolved and we can't distribute through. So what I want to point out to you is if you have more than one term in the denominator separated by plus or minus, you're stuck. You really can't do any movement. So that's a quick giveaway, where if I have more than one term, I always want you to do a power rule conditions check, but this is a quick indication that, okay, this option is out. I'm stuck with this form. Now, if there's only one term in the denominator, then we can separate that into individual fractions, or we can move it up much more easily. We can distribute, no problems. If it was, as long as the monomial like 3x squared or 4x to the 1/2, we're good. But anytime you see a plus or minus of separate terms, we know that our first option is never going to work. Now, second option is U substitution. Okay. But if we want to explore U substitution, notice that this is not as easy as what we did for chapter 4. Chapter 4, I said, hey, just get a set of parentheses to show up, and that's most likely where U value is. Parentheses is not as apparent here, so we're going to have to kind of play around with what our U value could be. So here's a couple of things that we're watching out for, or we're looking to do. We want to be able to assign a U value so that our problem turns into an expression that matches a rule that we have available. And we want all the x's to go away, cancel out. Okay, so we're kind of playing, we kind of have to figure out where that path is, right? So let me list out a couple options. And I think the difficulty is there's no like hard and fast rule where, okay, the U value is always here. It's going to depend on how the problem looks, but I can kind of give some general guidelines. So let me list out some options there. So maybe our u value is 2x. Maybe our u value is x squared. Maybe our u value is x squared plus 1. So if you had to guess, right, I don't expect you to guess everything right the first time, but let's just go through this process together. If you had to guess, what could be a good place to look for, or what could be a possible u value?
X squared plus 1.
X squared plus 1. Okay, let's talk about why this is a better fit than the other two. The 2x is not ideal because the degree is not great, right? We saw from before that things will work out better if we let the u value start with a higher degree. And also, if you're choosing between numerator and denominator, usually, okay, again, this is a guideline, usually the denominator is a better fit for the u value than the numerator. It's tougher for the denominator to cancel out. So the degree is an issue, the location is an issue. So 2x is not great. X squared, I think some of us may think that's a good fit because the degree is ideal, right? X squared is a good fit because the derivative will handle that 2x. But here's the issue. The issue is that we have not allowed the u value to be a significant portion of the problem. If you just let the u value be just x or just x squared, what's happening is you haven't changed the problem a lot. We want this problem to look a lot simpler than where we started. That's the whole point of U substitution. So usually you want your u value to be just more than a term. It's usually going to be multiple terms because that will allow your problem to clean up faster and match a rule easier. So x squared is not going to be quite enough. So that leads us to x squared plus 1. Okay, it's a significant portion of the problem. The degree is a good fit, and we're hoping that it'll match with one of our rules. Okay, so I don't expect you guys to be able to see, the entire way without working through it. And so it's just a matter of the more practice we do, the more we can look ahead, the more we can predict what's going to happen. Okay, so let's start with that. Just like before, we're going to be targeting what we think is the u value, and we're going to be targeting the dx. We're going to leave the remaining portion alone and see how things play out. Our u value is x squared plus 1. Derivative, 2x. Cross multiply. Divide both sides by 2x. All right, and then now we're making our substitutions. Bring everything else down that we're not going to substitute. 2x stays. Denominator becomes my u value. And dx becomes du over 2x. So what do you see? Good. So the x is what's important, right? The x, we definitely need to cancel out. Okay. So it's nice that the 2 also cancels out. So we achieved our first goal, right? The x is to go away. And the second goal is, just because we have everything in terms of u, doesn't mean that it's going to match with the rule that we have, but thankfully we have a rule that matches with the rule that's available to us. So we can apply our rule. 1 over u becomes natural log absolute value of u plus c. Remember that u is only a temporary variable. So we're going to sub that out. Remember that the x squared plus 1 is inside the natural log function, so we can't distribute this through, right? This is not a standalone term. This is connected all within one function here. Okay, any questions? Yeah, so the challenge that we're going to be experiencing is finding that u value, right? And there's no hard and fast rule. We kind of have to just look ahead as much as we can and hoping that we can look far enough where we can decide whether we're going down the wrong path before we get too far down that path. Number 2, integral of 1 over x natural log of x. First thing is we want to look at our first option. Do these power rule conditions work? And we already see that there's an issue, right? Natural log of x doesn't even fit as, we don't have anything for natural log of x here. So we know we need to involve a more complex rule here. So we know this is out. Second option is U substitution, but it's not very easy to know where that U value is. Right? There's no parentheses that we can quickly identify. So let me list out a couple of options, and then you can tell me what could be a good possibility to help move us forward. Maybe the U value is x. Maybe the U value is maybe it's 1 over x. I'm just looking at combinations here. Maybe the U value is just natural log of x. Maybe the U value is x natural log of x. Any guesses? So we want to select the U value that will allow the remaining x's to disappear, and we want the U value, and we want the problem to look like a rule that we have available.
1 over x, maybe?
1 over x. Okay, let's talk about that. 1 over x, if I let the U value be 1 over x, the derivative of 1 over x is not going to get us natural log of x. Okay, so I mean, it's good that we're picking a significant portion of the problem, but if we look ahead, we're not going to get that pairing that we want. So, okay. Okay, let's explore this one here. The good thing about x natural log of x is that you're picking a significant portion of the problem. That's a good start. Also, you're picking the denominator. That's also good, right? If you're choosing between numerator and denominator, you let the denominator be the U value. But let's talk about this here. If I let my entire denominator be the U value, what would happen with the derivative? What process would you go through to find the derivative of x natural log of x? Product rule. So if you think about product rule, that's a pretty messy thing, right? F prime g plus f g prime. Do you see anything here that will be a match with the derivative of x natural log of x? Yeah, there's not enough, right? There's not enough to pair the derivative of our U value. So it's a good, I mean, it's a good guess because we're doing the things that I've been stressing, which is looking for a significant portion of the problem, but it's a little too much, okay? It's a little too much, and that leaves us with what?
Natural log of x.
Yeah, let's try natural log of x. Again, some of you may be thinking U equals x. If I do U equals x, you do convert everything to be in terms of U, but this is not enough, right? So you're usually looking for something more than just a simple variable change, right? You're not making any progress if you're just making a simple variable change. Okay, let's explore what happens with that natural log of x. So I will underline this, and I'm hoping that through this process, this x will take care of itself. We'll see. U value is natural log of x. The derivative of natural log of x from first semester, we learned natural log of u becomes u prime over u. So du dx is equal to what? 1 over x, yeah. cross multiply to get that dx by itself. And we're ready to make our substitutions. Replace natural log of x with u, replace dx with x du. Do things work out here? Yeah, the x's cancel out. I just got done saying that it's harder for something in the denominator to go away. But natural log of x matches that, allows that to work because the derivative of natural log ends up with a variable in the denominator. Usually, when we think about derivative of terms, we usually don't have many rules giving us a variable in the denominator. But natural log does, and so that allows for a location of that x to be suitable for us to work things out. X just goes away. We're left with everything in terms of u. We have a rule that matches this perfectly. So there's our natural log rule. Finally, remember u is only a temporary variable. Replace the u back in terms of x. It's strange seeing a natural log inside a natural log, but that's what happens here. So again, in the grand scheme of things, what we found is we found the antiderivative, which is essentially an area formula for whatever is under this curve. We can, if we have bounds in this problem, we can use this function to find the area of any region under whatever this graph looks like. Okay. Questions so far? All right, let's skip number 3 for now, because I realized with number 3, it's better to handle number 3 after I've talked about the process that I want to show you on the next page. So it's a little bit out of order. Let's go to number back page here. More trig integrals. So we have those integral trig rules that you used on the test. They're just coming originally from the derivative rules that we learned first semester. But we also have these additional trig rules that are not the original 6. And these exist where the integral is involving natural log. We just have to be able to recognize it and be able to use it. But really, it's just following the rule. I do want to go through an example to show you that we can derive tangent, and we're going to prove that this statement is true using another form of this problem and working our way through U substitution. But that's just to demonstrate that this where this rule is coming from. On the test or quiz, you're not going to go through a deriving process. You're just going to jump to the rule and use it. But we'll just do example 4A just to see that connection and also just get some additional practice with U substitution. All right, so think back on trig here. What's what's equivalent to tangent that we know? What's a trig property that we know? Sine over cosine. So we know these are the same things, but if we have two functions, we can potentially go through a U substitution phase and see where that leads us. Okay, we know we can't handle these rules separately. We have integral rules for cosine, we have an integral rule for sine, but we know that's all out the door if they're divided by each other, right? We can't just pick and choose different rules if they're connected by division. So let's go through U substitution. And if you're having to stare at numerator and denominator and they look like they both could work in terms of the derivative of each other, go after the denominator. The denominator is just naturally going to fit better when you're ready to cancel things out. Okay, we'll let the U value be cosine of x. Just as a reminder, the derivative for cosine is negative sine, and on the test or quiz, I will, just like on the chapter 4 test, I will have that formula sheet ready for you attached so that you can have easy access. Cross multiply. Divide both sides by negative sine of x. And the placement of that sign is perfect because we should be able to get that numerator sign to go away after we make our substitutions. Sin x cancels out conveniently. Careful with the negative, got to keep track of that. So I'm left with -1 integral of 1 over u du. And we have a perfect rule that can handle this, which is natural log. U is a temporary variable. Replace the u back in terms of x. And now, if you look, this rule or this solution matches exactly with this rule that we're going to be using. But we're able to derive it using sine and cosine. Cotangent, I'm not going to go through the whole thing. I'll have this on my key, but same process here. But instead of sine over cosine, we know cotangent is cosine over sine. Process is the same. We let the u value be sine of x, and we'll be able to work our way through and get that natural log of absolute value of sine of u plus c. And we just go through the same process. So you guys can work this through at your own time if you like, but in the interest of time, I'm going to go to example 5. Okay, questions so far? Okay, let's look at example 5 and talk about how this is different than the ones we've experienced up to this point. Okay, I'll put this on a separate sheet just to make it larger for us to see. All right. Back to the beginning. Can I rely on power rule conditions to get to where I want to go? Right. This is a quick way of telling, right? Denominator, too many terms. Okay, we can move on, right? This option is not going to be possible. All right, so next option, U substitution. Maybe we can pick between numerator and denominator. Do you see a u value that could fit?
Maybe x plus 5.
Maybe x plus 5. Okay, so that's a good spot to look at. The denominator is a good spot. But what's going to make this challenging? Yeah, degree is not ideal, right? Maybe you're thinking, well, what if we go through change of variable? But that is maybe too much for us to ask for it to work out. So we looked in the right spots. Denominator, degree is not ideal. We're not going to get things to cancel out. U substitution in this form is not going to get us very far. We're going to get all these x's left over and no way to cancel those out. So we need to explore something else, right? And so this is the third option, or this is we're going to add to this checklist that we're building here. And this is a long division method here, or long division problem. So the purpose of long division, right, is not going to help us solve the problem, but it will give us a different version of the problem. It will give us a different form of the problem that hopefully will lead us to something that we can actually work with in terms of because our integral rules are so restrictive that we have to kind of get it into that specific form before we can use it. So long division is not going to solve it, but it will give us a different version or different form of this problem. So we're going to practice getting that form. Something else that we can come back to is the way that we can tell that long division could possibly be a good fit is, after you go through your checklist, you realize that your numerator has a higher degree, at least the same, if not higher, than the denominator. Okay. So basically, we know this long division could be a good fit if the numerator degree is greater than or equal to the denominator degree. Because usually if the denominator has a higher degree, then we want to really explore U substitution. We're hoping that will be the way to get there. But if the numerator has a higher degree or the same degree as the denominator, long division, or we're going to talk about synthetic division as well, it could be a possible way of getting to where we want to be. So here's the process. We're going to divide this out. We're going to use this division notation here, or this division symbol. So we're going to divide the x cubed minus 6x minus 20 divided by the x plus 5. And our quotient is going to represent a different version of the problem, and then we can solve this problem once we can get to this form. Okay. You've seen long division before, but we're going to go through it go through it like as if you haven't seen it. Okay, I'll go through it step by step. Now, the first thing we do is we look at the first terms within each of these sections. And we're going to ask ourselves, x times what gives us x cubed? X squared. And whatever the answer to that question is, you're going to put that above the line. And you're going to take that x squared, and you're going to distribute it through the divisor. And you're going to put the result below the dividend terms. So x squared times x is x cubed. 5 times x squared is 5x squared. Good so far? As soon as you do that, you're going to do a couple things. You're going to draw a line, and you're going to change the signs of the terms that you just brought down. So if it's positive, make it negative. If it's negative, make it positive. So these are both positive terms. I like to circle my new signs, so as to kind of help me focus on the sign of, because it's just a little bit easier to highlight when I have it circled. Now we're going to be adding like terms with what we see. Your first terms will always match and cancel out. X cubed minus x cubed, that's what we always expect. Now the remaining terms, we may have like terms, we may not have like terms. We just got to be careful. Okay. If we have like terms, we can combine and bring them down. If we don't have like terms, we got to bring them all down separately. So what do you see? Any like terms? No like terms. So we're going to bring them all down. The way you bring them down is you bring them down in descending order. So start with the highest degree and then move your way down to the constant. So my highest degree is the negative 5x squared. So I'll bring that term down first, followed by the minus 6x, followed by the minus 20. Okay, good so far? We're going to cycle back and repeat the process that we started with. Look at the x, look at the negative 5x squared, and we're going to ask ourselves, x times what gives me negative 5x squared? Negative 5x. You're going to put a negative 5x, a minus 5x, next to the x squared. Now, we're done with the x squared, so cover that up, and you're only going to distribute the negative 5x through the x plus 5. And you'll put that result below. So negative 5x times x is negative 5x squared. Five times negative 5x is negative 25x. Draw your line, change the signs of the terms that you just brought down. Negative becomes a plus, negative becomes a plus. Add, when you add, you should get a perfect match. Your first term should go away cleanly. Do we have like terms here?
Yes.
Okay, and what do we get?
19.
19, positive 19x, right? 19x minus 20. Okay. Cycle back to the beginning of our process. We're now looking at x and 19x. X times what gives me 19x? 19. Cover up the x squared and minus 5x. We're done with that. We're just going to distribute the 19 through the x plus 5 and put it below. 19 times x is 19x. 5 times 19. You know that 5 times 20 is 100, so 5 times 19 is just going to be 95. Draw your line, change your signs. First term matches and goes away. Negative 20 minus 95, like terms. Negative 115. All right, back to our beginning here. X times what gives us negative 115? Can I go any further? Okay, so this degree is too low. It's below what our divisor is. We can't go any further. This is the leftover. And what do we call leftovers? The remainder. Now, there's a specific way that we write the remainder. We want to indicate that I can't divide negative 115 by x plus 5 any further. So I'm going to do exactly that. I'm going to say my remainder is my term divided by the x plus 5. I can't go any further. This is as far as I can go, and I'll just indicate that as my remainder. Now, we haven't done any calculus yet. We did all that just to get to the point where we can have a rule that can handle this problem here. But any questions so far about this process? This is a messy process. We have synthetic division, which is a much faster way to get to this here. But we have to understand the shorthand method, which I'll go over with you. And also, synthetic division comes with some restrictions. It can only handle very specific types of problem. Long division, it is cumbersome, but it will handle all the types that under this category, under this umbrella. But we'll do it one piece at a time. Now, this is the same thing as this in terms of the value. But we're going to have a much easier time finding integral rules here than here. So I'll go down and we will look to find the antiderivative of our new form. Okay, so this is the result of long division, but what do you notice? What's nice about this form that we didn't experience before? Yeah, all these are nice and clean. These are all separated. Nothing is dividing with this. There's no parentheses. There's no multiplication. These are nice, clean power rule. What about this? So what do you think we can explore with this problem? Good. This is going to be a simple U substitution problem. So we'll do power rule, power rule, power rule, and we'll do U substitution here. Let's do this one first. This is the more complex one. I want to show you that, yes, this is U substitution, but hopefully this is a rather, I guess, simple U substitution. So the hope is that after you get comfortable with the process, you can jump from this to the antiderivative without having to go through all these different notations. But, you know, only do that jump when you feel like you're ready and you feel comfortable. But I'll go through the full process here. So we're going to solve this problem. We're going to pretend like this is its own separate problem. Okay, so I'm moving this. I'm moving it over here. All right, if I want to go through U substitution, what's my U value? X plus 5. Okay, so we'll target this. Okay, du dx equals 1. The good thing about this, or the easy thing about this, is we're not going to have any leftover coefficient we got to keep track of. It's just going to be a clean dx equals du. We make our substitution. I'm going to pull the negative 115 out. And I'm left with 1 over u du. This is just natural log with the coefficient of negative 115. And then replace the u back in terms of x. And this is the antiderivative of this. Okay. Any questions? Now, let's finish the rest of the problem here. Let's do power rule, like what you guys said, for the first 3 terms. X squared becomes?
X cubed over
Minus 5x becomes?
negative 5x squared over 2.
Good. 19 becomes?
19x.
Good. Right. Don't make it go to 0. That's derivative, right? We're going the other direction here, antiderivative. We found this, which is minus 115 natural log of x plus 5 plus c. There's our antiderivative. The hope is that down the road you can save some time. If you see this rather simple problem, I'm hoping that you can jump from this directly to here without having to go through this whole thing. But, you know, keep doing this until you feel comfortable with that jump. But once you're comfortable, you can go from here to here without having to go through all these notations here. Okay. All right, any questions? Okay, I didn't get a chance to go through example 5b, which is synthetic division. So I will do that at the beginning of class tomorrow. I'll also show that we can go through one of the methods that we just learned with example 3. So we'll finish up with 5.2 at the beginning of class tomorrow. And then we'll start 5.4 with exponential function e to the u. Yeah, just continue to make progress, getting ready for our quiz, which is next Tuesday. All right, thanks everyone. Hope you guys have a great day. See you tomorrow.